In previous chapter, we have seen first order TET versus second order TET element, and we understood that second order elements are more accurate while capturing stress concentration zones. In this chapter, let's see the second order TET versus first order hex elements. Let's try to understand this with the workshop. So I am going to take or continue with the previous problem where we had used C3D10 elements with the 0.5 mm element size in this region. Okay, before let me show you one thing. In PrePoMax, you also have element quality check. You can go to model element quality. Here there are so many mesh quality indices are there. The mean Jacobian is minimum determinant of Jacobian. This is maximum determinant of Jacobian, and this is minimum scale Jacobian. Similarly, there are so many geometry shape parameters are there. So we can check minimum determinant of Jacobian, and we can see here there are some bad elements. So let's try to see how we can improve them. We can use this mesh optimization for second order elements. And now with this, let's see the parameters. Okay, now a few bad elements have improved, uh, but there are still, we can see some more improvement with some other optimization algorithms or meshing algorithms. So here we are not going into the details of meshing algorithm, but it is kind of a trial and error. Okay, for you the some or other algorithm will work and give better quality. So I'll use 2D meshing algorithm as automatic and 3D as initial mesh only, whereas I will keep mesh optimization. Let's see the qualities. Now this element looks better. So the purpose of this is to show like you can also check element qualities here. Okay, let's continue and focus on our objective of second order TET versus first order hex elements. Okay, so I'll submit, let me save this in a separate folder. So I will be working on this folder C3D10 versus C3D8, okay, second order TET versus second order, sorry, first order hex elements. So let me run this model. So we have seen the analytical value of peak stress is around 322 megapascal. Okay, this is the 324 megapascal. However, these values are extrapolated stress values at the nodes. As we know, the accurate values are at the integration points. So let me show you one thing how we can also request integration point output. You can go to history output. I have already created, so I'll just show by opening this. Okay, we can create element output and select the domain where we want integration outputs. Here I have selected entire part, and variables to output is as stresses, and I will say okay. So this will give me output at integration points. Now let me go to the results. Okay, now here you can see history outputs, okay, which is coming from this history output request. This output is all six trace components. So we can see it in terms of table. The same output is also printed to dat file. So let's open the dat file in our work folder. Okay. So before that, the one message trace, okay, which is uh, our quantity of interest is also S11 because major stress in this local region is uh, X direction stress. Okay, that is S11. So we'll be focusing on S11. Let's see the output in that file. Okay, you can go to the work directory and you can see here .dat file. So if we see this, there are the stress outputs. Okay, the first column is element. Since this is second order TET elements, one element has four integration points. So one element, 1, 2, 3, 4 integration points. Similarly, element number 2 and four integration points of element number 2. So all the elements have four integration points, and we get four set of output or stress outputs at a single element. Okay, so let me copy this and check these outputs in Excel file so that I can show you the maximum output peak stress, okay, at any integration point, basically near our local region. Okay. So this is a element number. This is integration points 1, 2, 3, 4 in this element. Okay, and this is S11, S22, S33, S12, three shear stress components. So let me go to end and find out the peak stress. So I am seeing S11. It is a 318 megapascal. So the purpose of this, no, to show you that though it is 324 or 325 megapascal, it is a nodal output which is extrapolated and averaged at the nodes. The real output is integration output, which is 318 megapascal, whereas uh, our analytical solution is 321 megapascal. Okay, so we are not exactly, we are not at the analytical solution with the second order TET elements of 0.5 mm. Okay, let me now, so let me note down this. C3D10, 318 megapascal peak stress. Let's do refinement here, and we will now use 0.25 element size. If you want, you can check element quality again. It looks okay. Since we are only using one element through thickness, so we cannot expect Jacobian more than this better. So let's go with this. This is fine. Let's create analysis TET C3D10 0.25 mm. Let's see the results. Okay. Now stress, as I said, we are not interested in this nodal output. Okay, so I will go to work folder and check the date file to see integration point output. Okay. So let me copy this entire. Now let's see S11 output. Now we are seeing 322 megapascal peak stress. So with 0.25 mm, we are getting 322 megapascal, which is equal to our analytical stress value. And we also want to see the mesh count here. So we can open this file, okay, output with the same analysis, but with output as a prefix. So first we will see the mesh count here for 0.5 mm size. We can see nodes 5k and elements are 2300, 5k and 2.4k. Let's note down this. So the first one is nodes, then this is element count. Similarly, with 0.25 mm element size, it is 8.2k, this is 3.9k. Now let's compare these C3D10 results with first order hex elements. I will save this model as hex C3D8 and will make necessary changes. Okay. So first thing I need to deactivate this. Okay. And I will use extrude mesh. Here I need to use this will extrude the elements. If I don't change this default, it will create wedge elements. So I need to use this one. Okay. Similarly, this and scale factor we can keep 1. We want one element in thickness direction. So you can also give some quality combine parameters here. Okay, so it is showing in which direction we want to extrude. Okay. By selecting the part, the direction, the algorithm shows the direction. So I'm okay with this. Okay. Let's mesh this part. Okay, so we are using 0.25 mm of element size. I will delete this. We can also check the element quality as always. So element quality are okay. These are very high aspect ratio, so these are showing as highlighted elements. But these elements are okay. There is this element is quite skewed element, but it's okay. We are not interested in this region. So let's go with this mesh. Let's create analysis for hex element with 0.25 mm element size. Let me run this and see the results. Okay, here we can see the peak stress is 325. Let's see integration point outputs in the dat file. Since we want to compare with our analytical values, we will compare with the integration, which is more accurate. So let's see what is the max peak stress S11. It is 322 megapascal. So we will say C3D8 here, the 0.25 mm. Okay, let's note down the mesh count. 4.3K and 596. Let's do one thing. Let's run C3D8 with 0.5 mm size. So I will increase the element size here. So let's create another analysis for for 0.5 mm element size. Okay, so let me check that file, and we will see the integration point output. So the peak stress is 318 megapascal, and let's also see the mesh count here, which is definitely very low number, 2.4K and 314. Now let's talk about observations. As we can see here, both the elements are giving similar peak stress, 318 megapascal and 318 megapascal, and 322 megapascal. However, we need to check the mesh count. Okay, Since this problem is very small, we don't actually realize the computational efficiency. But as the model size increases, we can see the hex elements perform better. Okay. If you see here, 0.25 element size of C3D10 and C3D8, it is almost the node counts are double for C3D8, C3D10, whereas element numbers are almost 8 times. Okay. So this is 2x and this is 8x. So we can conclude that hex elements, first order hex elements, provides a solution of equivalent accuracy as C3D10, second order TET elements, but at a lower cost because we can see the mesh count is very less. As we know the nodes, number of nodes here we have 4.3k, so the degree of freedom is 3x since these are solid elements. So our element stiffness matrix size is 12.9k, okay? 12.9k by 12.9k, whereas for C3D10 it is 8.2 into 2 is 16.4. Okay? So the number of degrees of freedom are sorry, 8.2k multiplied by 3, okay, which is 24.6k degree of freedom. So our k matrix size is 24.6k by 24.6. So we can see that the computational resources required for C3D10 is higher, okay, because stiffness matrix is of a double size in this particular case. So we realize this computational benefit when we are doing nonlinear analysis. Okay. Since this particular course is not on nonlinear course, so it is out of scope. But in nonlinear analysis, as you might know, the stiffness matrix gets updated at each iteration. Okay. So this the computation becomes more expensive in nonlinear analysis because stiffness matrix is bigger in case of C3D10 elements. So we can say C3D8 elements, hex elements provides equivalent accuracy at lower cost. Okay, so these are the summary of today's exercise. TET elements are geometrically versatile. That means the TET elements are very convenient to mesh any complex geometric shapes, and that is why they are more popular. But on other side, hex elements provide equivalent accuracy at less cost. So as much as possible, we should use hex elements. If the shape is not feasible to mesh with hex elements, then we can go for second order TET elements. Other thing is that as this course is not on nonlinear, as I said, so we are not going to discuss this, but hex or quad elements provide better convergence rate for nonlinear analysis than TET elements. However, the hex elements perform better if their shape is approximately rectangular. So we need to maintain the shape of hex elements as much as rectangular as possible. And there are some modeling issues with hex elements in bending problems. Okay, we will see this in next sections. We will see these issues and also their solutions.